Sometimes we may have to conduct hypothesis tests to compare mean values of more than two groups created by using factor. Based on number of factors, we can call this ANOVA as one-way ANOVA or two-way ANOVA. In one-way ANOVA, only single factor is taken into consideration. Means all those means are created by using single factor. In two-way ANOVA, two independent factors will be considered. In our course, we will see this one-way ANOVA. One-way analysis of variance is a technique that can be used to compare means of two or more samples. Those samples are created by using a single factor. That is the reason we will call it as one-way ANOVA. Suppose if we want to study the effect of three levels of fertilizer on plant growth. Here A1, A2 and A3 are the three levels of the factor being studied. Here we have only one factor, that is the fertilizer, but which is applied on three levels. So we will get three means. We need to compare those three means. We already seen t-test, which can be used to compare two means. If you want to compare three means, we can use this t-test multiple times to compare those means. Here we need to compare these three means. If we perform t-test between mu1 and mu2 with alpha, suppose 0.05, and second t-test between mu2 and mu3 with alpha again 0.05. This is test 2, and again we need to do one more test to compare mu1 and mu3, which is test 3, again alpha 0.05. The cumulative alpha level would be more than 0.05. So it is inappropriate to use multiple t-tests to compare more than two means. Let's see that in detail. When we try to compare means of three groups A, B, C using t-test, we need to implement three pairwise tests, A versus B, A versus C and B versus C. Similarly, if comparisons are required for k times and alpha is 0.05, then cumulative alpha value would be for all those 1 minus 0.95, or if we use k times would be k. Let's take an example. Suppose if we want to calculate probability of one or more heads. For two coin flips, the probability of all tails is 0.5 into 0.5. It will be 0.25. You have to subtract this from the total probability 1. So, if the coin flipped 3 times, the probability of one or more heads is 1 minus 0.5 3 times. So 1 minus 0.5 over 3. The result is 0.875. You will get one or more heads around 87% of sets of 3 coin flips. Similarly, for statistical test with alpha 0.05, if the null hypothesis is true, then the probability of not obtaining significant result is 1 minus 0.05, that is 0.95. Significant result means where null hypothesis will be failed. If we take 95% confidence level, this entire region 95% would be in favor of null hypothesis, remaining 5% will be in favor of alternate hypothesis. If result statistical value falls within this rejection region, then we can say that results are significant. Not obtaining significant result would be this 0.95. Multiply this 0.95 by the number of tests to calculate the probability. If not obtaining one or more significant results across all tests, it would be 0.95 3 times. The result is 0.857. Subtract the result from 1 to calculate the probability of making at least one type 1 error with multiple tests. 1 minus 0.857. The result is 0.14. Actually, we want alpha level 0.05. In each individual test, we use this 0.05. But when we applied multiple tests, then cumulative error level 0.14, which is far higher than this 0.05. So, to compare more than two means, if you use multiple t-tests, you will end up with wrong type 1 and type 2 errors. So, for comparison of more than two means, one-way analysis of variance is the appropriate method instead of multiple t-tests. ANOVA can only perform when independent variable is normally distributed. We already seen how to test this normality, and second condition is homogeneity of variance, means the variance within each group are equal. And third one, independence, means that the subjects in one group should not affect the subjects in another group. We know that to compare more than two means we use ANOVA. You might get doubt. To compare means why are we using method which is based on variance? Because the relative location of several group means can be more conveniently identified by variance among the group means than comparing many group means directly. ANOVA assess the relative size of variance among group means compared to the average variance within groups. To understand this statement, let's see next slide. Here we have two cases. In this first diagram we have three groups with means 8, 10 and 12. In this diagram B we have again three groups with means 8, 10 and 12. See here, distance between this group means from 8 to 10 to and 10 to 12, it is 2. Here also same distance among these three group means, but within group variance for these three groups is smaller. Here variance is very small. From this mean all other values are varying very less. When we compare here, mean is the 8 and variation is more. For these three groups, within group variance is more. For these three groups, within group variance is small compared to these three groups. Here within group variance is small, so we can consider these three group means might be more distinct than these three group means, because here within group variance is large. So ANOVA uses the ratio of between group variance to within group variance. Here if we take ratio between group variance and within group variance, here within group variance is more, so denominator value will be more. Ratio result will be small for these groups. When you see here, between group variance is same as this, but within group variance here it is small. Denominator value is small and numerator value for both groups is same, suppose x. ANOVA will use this ratio to compare means. For more clarity, you can imagine like this. Here, this is the between group variance, and from this mean to here, this is the within group variance. When you compare this within group variance with this between group variance, it is very small. But if you see in this case, between group variance is very small. This mean to this mean. Here also, this mean to this mean. Between group variance is small, but within group variance, which is large, from mean to up to here. So we can say that these three means are different, but these three means difference is very small. So you can consider all these three groups might be from same population. See here we have three groups. This first group mean is this one, second group mean is this one, third group mean is this one. Overall mean is located here. Overall mean to first group mean difference. This is the between group variance. This is between group variance to second group, like that. Within each group we have some small variation. So this is called within group variance. When you compare this within group variance with this between group variances, here between group variance is large compared to this within group variance. So you can easily separate these three groups. Here we have three groups. This star mean suppose located here. From this mean all other values are located too far, and this is the overall mean of all three groups. Here this intra-group variation is too high when compared with the intergroup variation. So nothing is gained by dividing these three groups, because these boundaries become ambiguous, and this group mean is not far from the overall mean. It seems that it would have been more efficient to explain the entire population with this overall mean than dividing these three groups. But see here, intergroup variance is very large when compared with the intragroup variance. Here intragroup variance is very small. The distance from this overall mean to the mean of each group is far, the boundaries between the groups become clear here. So dividing these three groups is more meaningful than dividing these three groups. In Anova problems, we will be using samples which come from the normal distribution. Suppose we have one sample like this here. Its mean is around here and within group variation is high here. Similarly, we have other two groups. To decide whether these three samples come from the same population or from the different populations, we need to calculate ratio of between group variance and within group variance. Suppose overall mean of all these three sample means is somewhere here, red line. To calculate between group variance, you have to find the difference between this overall mean and each individual group mean, and you have to take the overall sum value. And to calculate within group variance, you have to take the variance from this each mean. Here, within group variances are more than between group variances. Between group variances represented with red lines and within group variance represented with black lines. Here, this within group variance is more. So, they might come from the same population. In this kind of scenario, F value will be small. The group means clustered together more tightly than the within group variability. This group means are closer. The distance between means is small. This one relative to the random error within each group. This is the random error within group variance. So we cannot conclude that these groups are truly different at the population level. Suppose we have three samples. First sample mean is somewhere here and second sample mean, third sample mean. Overall mean of all these three samples is around here, this red line. Between group variances, this red line, this difference and this one. Sum of all these differences is the between group variance. Here variance within the group is small, represented with these block lines. The ratio of this between group variance and within group variance here would be high because the denominator value is small compared to the numerator value. So we might conclude that these three groups might come from three different populations. Here we have high F score because this denominator value is small and numerator value is large. The group means are spread out more than the variability of data within groups. These group means are more spread out than this within group variability. In this kind of scenarios, F value will be high. The distance between means here it is large compared with the random error within the groups. So we can conclude that differences between group means reflect differences at the population level also. So overall we can say that if within group variance is small when compared with the between group variances, we can conclude that those groups are different. If within group variance is huge and between group variance is small, then we can conclude that that variation is because of sampling error or it might be random error. So in that case we cannot say that those group means are different. Let's take one example to understand why we are taking the ratio of between group variance and within group variance. Suppose if we give three different health drinks for babies around age 1 year, if we feed the health drink one for the first group and their heights in centimeters are like this: 62 centimeters, 63, 65, 64 and 66. And if we feed the second health drink for another group 2, and their heights are 70 centimeters, 71, 73, 70, 75, and for the third group their heights are like this. If we observe here, even within this group also we have some variation within their heights. Within this group also some variation within group and even in this group also. The first group average height is 64 centimeter, second group average height is 72.5 centimeters and third group average height is 78 centimeters. Here the difference between groups is more when compared with the variation within group. Here 4 is there, and here we have more variation. Group to group variation is more, but within group variation is small. So we can say that this health drink affect the baby's height. Suppose even if we feed the same health drink for all these three groups, if we feed the health drink 1, then their heights are suppose like this. If we take the first group average height, suppose it is 71.2, and second group 70.8, and third group 72. Here also we have variation between these groups, but this between group variation is very small compared to within group variation. Here we have within group variation 8, and here between group variation is very small, below 2, and here within group variation is more than this between group variation. So we can conclude that when factor like health drink influence the heights, their between group variance will be more and within group variance will be small. If health drink doesn't affect the height, then this between group variation will be small and within group variation will be high. That is the reason we are taking the ratio of this between group variance and within group variance. We can say that this within group variance is the random variance which might cause due to sampling bias or some random error. This between group variance which is actually caused due to the factor like health drink. So we will take ratio of this between group variance and within group variance in ANOVA. Let's see one example for this ANOVA. Here 3 levels of fertilizer used on plant. Suppose if we had 6 observations for each level like listed in this table. For first level we have these observations, second level fertilizer, these observations, and third level. These are the observations for third level. Here only one factor, that is the fertilizer, but which is used in 3 different levels, A1, A2 and A3. So we can use one Way Anova. Here null hypothesis is all 3 means are equal. Alternate hypothesis, not all means are same, means either mu1 not equal to mu2 or mu2 not equal to mu3 or mu1 not equal to mu3. Any one of these conditions is true. To solve this ANOVA problems, we need to find the F-score, which is the ratio of between group variation by within group variation. We need to find this ratio. So first let us calculate each group mean value. Here for this first group mean value is 5, for this second group mean value is 9, and this third group mean value is 10. To calculate this mean, you have to sum all these values and we need to divide with number of observations. Here it is 6. Then you will get this mean value, and we need to calculate the overall mean. 5 plus 9 plus 10 by 3. Overall mean of all these 3 means is 8. Now we know the overall mean. Now we can calculate between group variance and within group variance. Let's calculate between group mean square value. Between group variation means just we need to calculate variation of all these values from the grand mean. Okay, instead of doing that, we can take the group mean of one group. We can subtract that from the grand mean and we can multiply that with number of observations within that group. Suppose n observations, we can multiply with n. That is what we are doing here. Here group mean, first group mean is 5, so we are subtracting this from this grand mean, and here we are taking mean square value, so square this value and multiply it with 6. Here we have 6 observations. Like that, repeat it for second group also. Second group mean is 9, so subtract this 9 from the overall mean, that is 8. 9 minus 8 square and multiply it with 6. Like that, repeat for third group also. 10 minus 8 whole square multiplied with 6. Then between group sum of square difference is this 84. Here we calculated sum of square difference, but we need mean square difference, so we need to divide it with degrees of freedom. Here we have 3 groups, so degrees of freedom will be 2. Between group mean squared value will be between group sum of squared value divided by degrees of freedom. Here it is 84 by 2, that is 42. This is the between group mean square value. And again we need to calculate within group mean square value. Within group mean square value means you have to calculate deviation from this group mean to all other observations. So let's do that. Here first observation is 6. You have to take the difference from the mean of that group, that is 1. Again second observation is 8. You have to calculate difference from the mean of this group. Like that you have to take the difference from this group mean for all the observations. Again repeat it for second group, 8 minus 9, 12 minus 9, like that. For this third group, 13 minus 10, 9 minus 10. If you repeat it for all observations, within group sum of squares is the sum of squares of all these 18 values in this table. So we need to square all these differences. So first value would be 1 and 3 square is 9. Like that, if you repeat for this 18 observations, the sum of squares for within groups is 68. We need to calculate within group mean sum of squares value. So find out the degrees of freedom. Here we have 18 observations. So degrees of freedom for this first group is 5, second group is 5, and third group is 5. So total degrees of freedom here it is 15. Within group mean square value is within group sum of squares by degrees of freedom, that is 68 by 15. Result is 4.5. Now we can calculate F statistic, that is the between group variance by within group variance, that is between group mean square value by within group mean square value. 42 by 4.5. The result is 9.3. After finding this F statistic value, find the F critical value. Numerator degrees of freedom is 2 and denominator degrees of freedom is 15. So critical value for numerator degrees of freedom 2 and denominator degrees of freedom 15 is 3.68 at alpha 0.05. Let's see that. This is the F table for the alpha level 0.05. Numerator degrees of freedom is 2 and denominator degrees of freedom is 15. This is the critical value 3.68. Now we can compare this F critical value with this F statistic value. Here F critical value is 3.68. it would be somewhere here. F statistic is 9.3, which is in the rejection region, which is far from the F critical value. So results are significant at the 5% significance level, means we can reject the null hypothesis. All group means are not same. So there is a strong evidence that the expected values in 3 groups differ.